Welcome to my podcast on kinetics of inhaled anesthetic agents. In this podcast, we will talk about the pharmacokinetic properties of inhaled anesthetic agents. Those are, as you know, sevoflurane, desflurane, isoflurane, uh, halothane. Sorry, my pen is giving me some problem. And nitrous oxide. And academically, you also need to know xenon. So we'll talk about the pharmacokinetics. That is what body does to these drugs. So first of all, before we go on to the pharmacokinetics of these drugs, there are certain things we need to understand about these drugs. Okay, so what we need to know about these drugs is, first of all, what is FA? What is FI? And what is PA? And what is PA as capital A, and what's PB. So you need to know what these things mean before I proceed and explain to you the concepts. First of all, what is FA? FA is fraction of the inhaled anesthetic in the alveolar gas. In other words, if alveolar gas is 10 parts and the anesthetic is 1 out of those 10 parts, the fraction would be 10%, right? Similar way, if anesthetic is 100, if the total gas in the alveoli is 100 parts and anesthetic is 20, then it's 20% or 2 out of 10. So it's a fraction of the anesthetic in the total gas mixture in an alveolus. What is Fi? Fi is the fraction of anesthetic in inspired gas. For example, if you're giving 3% sevoflurane to the patient, the Fi is 3 parts per 100 parts. In other words, 100 parts of the gas mixture, inspired gas mixture, has 3 parts of the sevoflurane. What is the PA? PA is a partial pressure of anesthetic agent in the blood, and is expressed in the units called millimeter of mercury. So if your anesthetic agent exerts certain amount of partial pressure in the blood, that's arterial blood, it will be expressed in millimeters of mercury and it will be called PA. What is P capital A? That's partial pressure of anesthetic in your alveoli. That is also expressed in the same units as pressure, that is millimeter of mercury. And then what is PB? That's a partial pressure of anesthetic in the brain. That's also pressure, so obviously it will be expressed as same units as millimeters of mercury. Okay, let me explain this concept further. Let's assume that you start inducing a patient with 8% sevoflurane. I assume that you have done some anesthesia in the past, like few weeks of anesthesia at least. And so you start with 8% sevoflurane. So in other words, and it is 100% oxygen. So you are adding, so your settings are 100% oxygen and 8% sevoflurane. So ideally, in this case, you are giving 92 parts oxygen and 8 parts of sevoflurane. So your Fi is 8%, 8 parts per 100, which is strict, it's a fraction, so it would be more of 8 divided by 100, that is 0.08. So Fi, this is what are you giving expressed in the percentage, and this is what you're giving expressed as a fraction. So at the same time, what is your Fa? What is the partial pressure, or what is the concentration of inhaled anesthetic in your alveoli? It's 0, because you just started inducing the patient, and patient didn't come from the floor inhaling some sevoflurane. So there's no sevoflurane in patient's lungs. So time t is equal to 0, your Fi is 8%, or Fi is 0.08, sorry, if you're a mathematician. I'm saying it slightly wrong. And your Fa is 0. Now, something else, very interesting. Let's start with a graph. Okay, let's start with a two-dimensional graph. This is a nice tool. I can draw straight lines. Okay. So, any graph, whenever you draw a two-dimensional graph, you have x-axis and you have y-axis. And on x-axis, you have to say what you are measuring or representing. So on x-axis, this time I'm representing time, and on y-axis I'm representing Fa. What's happening here? Sorry, it's technology hitch. Fa. That's the concentration of, or precisely the fraction of inhaled anesthetic in your alveolus. Time t is equal to 0, we know it's 0. As patient keeps on inspiring the gas mixture, the Fa, that's also a measure of concentration, keeps increasing. Then it reaches a steady state here. After some time, it reaches a steady state, and it does not increase anymore. And at this time, it reaches its maximum concentration. This is what you're giving in the gas mixture. So at this point, Fa becomes equal to Fi. It cannot increase more. So it becomes equal to what you're giving. So once it becomes equal to the inspired concentration, it reaches a steady state. This is a very interesting graph. So if you are giving 3% sevoflurane, let's say 1, 2, 3, 1%, 2%, 3%. Again, mathematicians would say that it's percentage, not a fraction, but it's very close measurement. So if you are giving 3% sevoflurane, let's write it here, Fi is 3%. Concentration will start increasing, and then when it becomes 3, it reaches a steady state or equilibrium. Okay. Now there's another way to draw this graph or represent this property. So we will still have a two-dimensional graph. Okay. Using this tool from iPad Pro. Okay, we still have a same concept. We still have x-axis and y-axis, and still time t on x-axis. So on y-axis, instead of Fa, we are actually representing, putting Fa by Fi, just to simplify it. so that we don't have to redraw the graph for every single different inspired gas concentration. So, and then I'm going to change the colors here, use the technology. Let's make it 1, let's make it 0.5 or half. Let's say I start giving sevoflurane. Same thing, concentration keeps on increasing, and once your Fa becomes equal to Fi, or in other words, the ratio becomes 1, this curve becomes a plateau. That's what you get. Now I am drawing the same curve for a different gas. Let's say blue, that's isoflurane. So as you start giving isoflurane, its concentration keeps on increasing. And then at time t, certain time, it becomes equal to the inspired concentration, or the ratio is 1, becomes a plateau. Now, this is important to understand. Let's say iso, let's say sevo. Now this is an important concept. You see, both curves more or less ended up in a plateau. But time it took for iso to reach a steady state or a plateau state is longer, which is this, than time it took for sevo to reach the steady state. So sevo reached the equilibrium faster than iso. And why? We'll come to that later. Let's have another gas, let's say brown, that is desflurane. So desflurane also has the same concept, but time it takes for desflurane to reach a steady state is even shorter than sevoflurane. And for completeness sake, let's have halothane in an orange. Time it takes for halothane is even longer than isoflurane. So if you induce the patient with all these gases from this graph, you will see that sevo achieves a steady state faster than faster than iso and faster than halothane. So rate of induction with sevo is faster than isoflurane and halothane. And halothane has the slowest rate of induction, and desflurane will have a fastest rate of induction based on this graph. We'll come to that why. As long as you understood this curve, I'm going to move to next one. This is dependent on the curve we draw, or the rate of induction. This is dependent on something called blood gas partition coefficient. So you have to understand this so that you can apply the concept that why rate of induction of sevo is faster than keep on saying des, why it's faster than iso, and why the curves look different. So what is a blood gas partition coefficient? Let's say you have in a lab a container which is full of blood. Okay. So it is full of blood. Let's say blood. This is blood. And then you dissolve a gas. Let's say gas is blue in the blood. So when equilibrium has reached, some of the gas would be, let's say you give a total amount of gas you dissolved or you put in a container is X. So some of the part of the gas, let's say Y, would dissolve in the blood. But some of the gas would stay in a gaseous form in an equilibrium. So if total gas was X, if Y has dissolved in blood, the gas that stays in a gas form is X minus Y. So blood gas partition coefficient would be amount in the blood divided by amount that's in a gas form. That means that did not dissolve in the blood. That's Y divided by X minus Y. Where X is the total amount of gas, Y is the amount dissolved in the blood. So if you have very soluble gas, that would have high blood gas solubility coefficient. Let's say this is blood gas solubility coefficient. Highly soluble gas would have higher blood gas partition coefficient. That is, more fraction would be present in the blood. Less soluble gas would have relatively smaller blood gas partition coefficient. So if I have two hypothetical gases, 1 and 2, and one has a blood gas partition coefficient of, let's say, 0.65, and another has a blood gas partition coefficient of, let's say, 2.4. This gas is more soluble than this gas. So when you inhale the gas, some of it goes from alveoli to the blood, and blood carries that gas away into the circulation and to the organs. So it constantly depletes the alveolus of the gas. More blood flow depletes more gas, less blood flow depletes the less gas. The graphical representation of this is, this is your hypothetical alveoli, and this is your blood flow, and I give you something called green gas. I am supplying the gas from a machine and blood, and the gas is carried away by the blood. So more soluble the gas is, more of it is carried away by the blood from the alveoli. Higher the blood flow is, more gas is carried away from the alveoli. So applying this concept, highly soluble gases would take time to build up. Okay, again, same concept. Coming back to redrawing that graph. Still working on the software. I don't know exactly how to retrieve the curve, but we can draw it again. Okay, so from this concept, highly soluble gases, such as halothane, for example, take long time for halothane to reach a steady state because blood is constantly carrying the halothane away from alveolus. So it will take longer time for halothane to reach a concentration of inspired gas mixture. Relatively insoluble gas such as desflurane takes actually reaches this equilibrium stage faster because it's very insoluble in blood. So blood is only carrying very little desflurane with each heartbeat or per unit time. So it achieves a steady state faster. Now sevoflurane is halfway between them. So it also achieves a steady state faster than halothane, but slower than desflurane. Then putting isoflurane here, somewhere here. So Now, if you understand this concept, we'll write it like with a pencil. So rate of induction, or I can also say time it took to reach steady state, where is a plateau, is dependent on blood gas partition coefficient. Blood gas partition coefficient. Okay? So, highly soluble gases that have higher blood gas partition coefficient, so the rate of induction will be slower. So rate of induction is indirectly proportional to the solubility, that is blood gas partition coefficient. More soluble gas, slower the rate of induction. Less soluble gas, faster the rate of induction. Now, when I say that, technically, ideally, I should also say other things do not change, provided the other factors do not change. So this is our conclusion from this lecture. Rate of induction is indirectly proportional to a blood gas partition coefficient. And you should memorize the blood gas partition coefficients of the commonly used gases, and you would see why sevoflurane induces faster than iso and halothane. But in clinical practice, we only use sevoflurane and halothane. That's something I will talk about later because of pungency and smell and other factors. Okay, now second concept is, we discussed that more the blood flow is, larger is the amount of the gas carried away from alveoli. So that tells us that rate of induction is also controlled by another factor. That is blood flow, which is measured as cardiac output, is also controlled by a cardiac output. Higher the cardiac output, slower is the rate of induction. Doesn't need a rocket science to understand that. More blood flow means more anesthetic is removed from alveoli, and hence longer it takes to reach a desired concentration in alveoli. Hence, longer it takes to induce the patient. So that's why young people take longer to induce than older people by gases, by inhalation induction. Now something very, very tricky here. Some of you must be thinking, and I better discuss it now than later. But before I go to the next concept, let me just summarize what we just talked. So we talked about rate of induction, inhalational induction is actually determined by the time it takes to reach a steady state, that is FAFI approximately 1.